Okay, so first things first, everyone pull up your chapter 3 worksheets. And as far as I'm concerned, we might as well do this in order. Like I said, I might skip question 2. Question 2 is just kind of tedious unless there's kind of an overwhelming demand to do it. But basically, you just argue that, yeah, no matter what you do, the best you can do is reproduce E, A, B, and AB. But let's start at question 1. I guess I'm getting ahead of myself. Let's start in question 1 and see if we can do it. And don't forget, this is an if and only if, right? So there's 2 things you have to prove. You have to, assume that the group is multiplicative, or you have to assume the set is a group and show that therefore n is prime. And then you need to do the other direction. You need to assume that n is prime and show that therefore that this gives you a group. And in both cases, there's really only one thing that you have to do. I'm going to give you about, it isn't if and only if, but let's say 6 minutes. Okay, I'll give you 6 minutes to give it a shot. And again, don't hesitate to ask any questions and I'll take them up in the chat, or you can just jump on mic. I'm happy to do that. Like I said, I'll take them up in about 6 minutes. Okay, so let's give that a shot and let's see where that goes. So any progress? Did anyone get both directions? Which direction was harder? Both directions were equally hard? Did nobody get anything? Maybe everyone got everything? Or are people just waiting for me to do the answer? Okay. All right, let's see what we have here. Oh, you know what? I should... Well, I appreciate the honesty. I really do. But remember, at some point, you're actually going to have to solve questions on your own, and you're not going to be able to wait for me to do the answer. So, right, you want to practice. All right, let's see here. Let's see if we can do that without hitting a button. Sweet. Okay, so the question says, so this is question 1. And basically, we want to show that Zn star is a group if and only if n is prime. Okay. Oh, I realize I can't. Okay. I'm actually going to start by doing this direction. And I'm going to show you why I'm going to start by doing this direction, just because I think it's going to make more sense when I switch directions. Okay, so I'm actually going to start by assuming that n is prime. Now, I only need to, of the 3 group axioms, associativity of the binary operator, the existence of the identity, and the existence of the inverse, I actually only need to prove one of these 3 things. Which of these 3 things do I need to prove? Okay, because I claim that the other 2 are immediate. There's nothing to do. Which of the 3 do I need to prove? Yes, Zn is the integers mod n, but you've removed 0. And Danny, exactly, we need to prove the existence of the inverse. So very quickly, let me say the identity is clearly in here. Multiplication mod n, the identity is the number 1. 1 is in Zn, right? Is multiplication associative? Yes, because it's associative in Z. So the only thing that we have to do is prove the existence of inverses, right? So we need only show that for every, what do I want to call it? We've already used n. I don't want to use p because that's prime. For every, let's call it z. In z n times, there's an inverse. Okay, does everyone believe that? Is everyone okay? Because if not, I'm happy to go into a little bit more detail, but 1 is certainly in the set and multiplication is certainly associative. We don't need to spend any time doing those things. We just have to do And that's what you should say, okay? If you were to actually do this as an exercise problem, you'd say 1 is clearly in the set, multiplication is associative, so we're just going to prove the existence of an inverse. Okay, so we want to show that there's some element let's call it W, such that ZW is equal to 1, right? That's what we want to do. That's what it means to be an inverse. So why is n being prime going to be important? Well, what I'm going to do is I'm going to suppose that W is any element of Zn star and say, well, because P is prime, the GCD of Z and W is 1, right? So fix Z in Z n times. Well, let's just say Z in Zn. No, Zn times. And note that the GCD of Z and N is equal to what? Is everyone okay with that? Because N is prime. Maybe let me add that in. Because N is prime, right? And the only way that the GCD of another number with a prime is not equal to 1 would be if Z were some multiple of that prime, but that's not possible because all of the elements of Zn times, Zn star, are between 0 and n minus 1, right, by definition. So every element in that group is co-prime to n. And in fact, remember when I was when we were defining UN, right, the group of units in Zn, we talked about how do you know if something is in UN? Oh, because it's co-prime to whatever n is, right? So the power of using a prime number is that everything less than it is co-prime to it. So is everyone okay with that? Are there any issues? Okay, yeah, this is a great question. What's the difference between UN and Zn? So UN is we're saying take Zn and throw away all the elements that don't have inverses, right? So maybe this is an aside here. So UN is equal to Zn times, but we've removed everything that doesn't have an inverse. Okay, and the intuition for this, which comes from that comment that I made earlier, is that the things that do have inverses are precisely the things that are co-prime to n. So the things with inverses are those elements of Zn, which are co-prime to n. And so that's where my intuition for this is coming from. For Zn star to be a group, every element of it, right? Every element needs to be co-prime to n. And the only way that's possible is if n itself is a prime number, right? That's our intuition. That's what we've got to use in order to help us figure out how to do this problem. So that's the difference between UN and Zn. Does that make sense? Did that help? Hopefully. Okay, great. So now we're going to continue. So knowing that the GCD of Z and N is equal to 1 by Bezout's lemma, which we love, there exists, let's call it R and S in Z, with ZR plus NS is equal to 1. Now, this is true in the whole natural numbers. What happens when I reduce this equation mod n? So if we reduce mod n, this becomes, right, just ZR is equal to 1. That's exactly what we wanted to show, right? We wanted to show Even though up here I didn't write them using the equivalence class notation, we wanted to show that Z had an inverse. And yeah, that's what I've done, right? I showed that Z had an inverse. Now, in my opinion, this is the harder of the two directions, right? Because you had to kind of have the forethought to say, oh, I need my elements to be coprime. And then not only do they need to be coprime, now I use Beswitz's lemma and then recognize that I need to reduce mod n. There's a couple of steps there, and it would have been easy to get stuck on any step. The other direction is much easier. Okay, so the other direction, I'm actually going to prove the contrapositive. So I'm going to suppose that n now is not prime. And I'm going to show that Zn star is not a group. Okay. Oh yeah, great. If you did this in 240, perfect. So the key here, again, remember, you still have the identity and you still have associativity. So the thing that must break is the existence of inverses. And the easiest way to break this is precisely using the fact that n is not prime. So since n is not prime, it's a composite number, right? Since n is not prime, let's write it as n is, let's say, r times s, for r and s not equal to 1 or n, right? So it's a properly composite number, or maybe let me say r and s between 1 and n. Maybe that's a little bit nicer, right? I can actually write it as, 6 is equal to 2 times 3 or something like that. But notice now we're done, because if we reduce this equation mod n, that gives us that r times s is equal to 0. 0 is not in Zn star. So the group operation is not closed. Or in particular, if r times s is equal to 0, neither of them can be invertible. So neither is invertible. And that's actually a great exercise. I don't know if you all can see this. This isn't an immediately obvious thing. Maybe you should prove it. It's only a line or two. But note, as a little exercise here, show that if r times s is equal to 0, and neither of these are equal to 0 themselves, then it's impossible for them to be invertible. Okay, it's a one-line proof. It's very straightforward. Sorry, my screen just went into screen saving mode and I thought my computer shut off. But it's one line. Okay, it's like 2 or 3 equal sign. It's very straightforward. It's a nice little exercise just to play around with the algebra. So I'd really emphasize that, give that a shot. See if you can do it. Okay, so are there any questions about this? Let me zoom out, try and get you the whole proof here in its totality, and then you can see it. But is everyone okay with that? Do you see how I did it? This question really relied on us understanding that the only way you have an inverse in Zn is that you are co-prime to n. Okay, this is critical. And this is a good sort of fact to have ingrained into your mind for this course. Okay, the only way that you have an inverse in Zn is if you are co-prime to n. And therefore, that's why primes are so important, because anything that isn't a multiple of your prime is co-prime to it, right? Okay, everyone's good? No crazy questions there? And if you're typing, just keep typing. I'm going to say, let's skip question 2. We can come back to 2 if we have time. 2 is, I think, a little bit, it's just kind of repetitive. It's just you literally exhaust all of the words, right? You write out all the words of A and B that you can, and then you convince yourself that you can reduce everything to A, B, the identity, or AB. And it's not terribly hard. You just really keep banking on the fact that the order of AB is equal to 2. So you can do a lot of things with it. So I say let's go to 3 because I think 3 is a little bit more interesting. It's not as tedious. That being said, if there's any great objections, if anyone really wants me to do 2 because you're like, I have no idea how to do it, then just speak out and I'll take it up. But otherwise, for now, let's assume that we're going to do question 3 next. Okay. So prove that a group G is a union of proper subgroups if and only if G is not cyclic. And for clarity, let's talk about what this question is saying. I mean, certainly G is also a union of, non-proper subgroups because it's a union of itself, right, with other groups. But we're saying show that it's a union of strictly proper subgroups if and only if it's not cyclic. This one is not terrible, but give it a shot and see what you can do with it. Okay, I'll give you about 5 minutes. Let me just resume my recording here. All right, so any progress on this? I think the first time I read this, I was a little bit confused about what it was asking. So, I mean, if there's a question about that, totally don't hesitate to ask. So again, I've kind of skipped question 2 and we're going straight to question 3 here. Like so. Okay. All right. So again, what's the question asking? So prove that G is a union of proper subgroups if and only if it is not cyclic. All right. So prove G is a union of proper subgroups. I feel like, for the sake of my recording, I actually probably should have done this before. Is a union of proper subgroups if and only if G is not cyclic. Okay. So let's do this direction. I'm going to do this one by contradiction. Okay, so I'm going to suppose that it is a union of proper subgroups, but that G is not cyclic. So for a contradiction, and that's how I always start my contradiction proofs. So for the sake of contradiction, I just like to tell the reader that I'm doing that right away. So let's suppose G is a union of proper subgroups, but G is cyclic. Okay, so in particular, it has a single generating element. Now, because G is a union of proper subgroups and it's generated by the element A, then in particular, A is in G, so it's in one of those proper subgroups, right? So since A is in G, it's also in a proper, and that's critical, a proper subgroup H of G, right? But then what that means is that the subgroup generated by A must also be a subgroup of H. Right? And the subgroup generated by A is all of the original group. So what we have here now is we have a double inclusion, right? H is a subgroup of G. It's supposed to be a proper subgroup of G, but now G is also a subgroup of H. So the only way this can happen is if H is equal to G. And that's a contradiction. Right? Since we assumed that H was proper. And now I've shown that, well, actually, if this is true, then that proper subgroup is not proper. It's actually all of G, right? So boom, we've done that direction. Now in the opposite direction, I'm going to suppose that G is not cyclic and show that it is a union of proper subgroups. And notice the union, it doesn't say finite union, it doesn't say countable union, it just says union. Now, this one's a little bit hand-wavy just because if you really want to write it out in full detail, it's a little bit messy, but let me give you the gist of how this is going to go, right? So let's suppose G is not cyclic. G is not cyclic. Okay, and let's just choose any element in there. And choose any element. Let's call it A1 in G. Okay, so in particular, the subgroup generated by A1 is not the whole group. A1 is a strict subset of G, right? So we can find another element, A2, which is not in A1. A2 be in G without A1, right? If G is the union of A1 and A2, then we're done. A1 union A2, we're done. Otherwise, note as well, right, that A2 can't be the whole group, right? Because if A2 were everything, then G would be cyclic. Otherwise, there's an A3. In G, not A1 union A2, right? And you can see the pattern. You just keep doing this, right? And G is not equal to A3. And so you just keep taking the union over all of these elements, and you've now gotten that each of these is proper, and union together must give you everything because you're just going to keep doing this, right? So in fact, you could just do this over every single element of G, I guess. You don't even need to choose something that's not or you don't have to choose something that's in G, not A1. You could really just take the union over all of G. So in effect, that might actually be an easier way now that I think about it. Let's take the union over G and G of G, right? All of these are proper, because if they weren't proper, if one of them is not proper, then the group is cyclic. And so we're done. Right? So it occurs to me that's actually a much better proof than just that last line. Okay, are there any questions about that? Everyone's okay? Okay. Next question, question 4. This one's pretty quick, so I might give you less time. Let me write it out because I said I was going to do that this time. All right, so this is question 4. So what is it? Suppose that suppose A and B are elements of G with coprime orders. Show that their cyclic subgroups intersect trivially. Right? Okay, I'll give you 4 minutes to try that, and let's see where that goes. Okay, so that's 4 minutes. Let's see what we can do. I want to emphasize this part is just fundamental theorem of cyclic groups, and it's very important that you be comfortable with this. Okay, because you can imagine, you've got a term test next week. What can we ask you about? Maybe some GCD nonsense, but who cares about that? That was just kind of review. So everything that we ask you is going to be about like groups and like cyclic groups and stuff like that. So this is the stuff that you really want to be comfortable with, right? Okay. So I want to show that these two things intersect trivially, and somehow the fact that their elements are going to be coprime. Yeah, right. October 8th is the term test. So it's next Friday. You'll be fine. What's the worst that could happen? right? I mean, you could fail. I guess worse than that is an academic offense, but you have complete control over the academic offense part. Okay, so anytime you want to show anything about the intersection, what do? You start by choosing an element in the intersection, right? Let X be in the intersection of A and B. So in particular, X is in A and X is in B, right? Alrighty. So somebody tell me, what can I say about the subgroup generated by X? All right, if X is in A, the subgroup generated by A, what do I know about the subgroup generated by X? All right, so now at this point, you should go to your notes and you should look up the fundamental theorem of cyclic groups. And what we know is that the subgroup generated by X will be a subgroup of the subgroup generated by A, and that the order of X must divide the order of A. Right? In exactly the same way, because obviously there's no difference between A and B in terms of this definition, we can conclude that the order of X must divide B. And make sure when you do divisibility and you're talking about orders, you make your divisibility sign very tall. Otherwise, there's just way too many vertical lines and you don't know what's going on. So we know that order of X divides the order of A, the order of X divides the order of B. What do I therefore know? Does anyone see what you should be able to conclude from this? If you divide the order of A and you divide the order of B, what are you? Right, exactly. X divides the GCD of A and B, right? X is a common divisor, right? It divides both A and B. So in particular, every divisor divides the greatest common divisor, right? But that was just equal to 1. Which means that the order of X is equal to 1. And there's only one element in the group that has order 1. And that's the identity. So what have I done? Think about what I did. I said, choose an element in the intersection. I proved that no matter what element you choose, that element had to have been the identity element. And so voila, we're finished. Okay, does that one make sense? Okay, now I don't think we're gonna have much time for question 5, so maybe let me just take it up and just very quickly show you what I would do. So in question 5, we want to prove, so this is like, I guess it's called A, let's call it A. So prove that the order of A inverse is equal to the order of A. And many of you are probably like, yeah, that seems pretty obvious, but how do I actually go about proving it? So for A, the way I would do it is I would do this. A inverse to the power of the order of A is the same thing as A to the order of A inverse. And if you haven't convinced yourself of this fact that you can interchange the power in the inverse sign, you should, and you should prove it. Okay, so make sure that you convince yourself that you can interchange the order of the inverse operation and the exponentiation operation. Okay, maybe that's a good thing to prove. But once we can do that, we get E inverse, which is just E. So what have I managed to do? You might say, like, this is a lot of work to show something that isn't really that important. Well, I've showed that A inverse to the order of A is equal to the identity. That can only happen if the order of A inverse divides the order of A, right? We know that if G to the M is equal to E, then the order of G must divide that exponent. And of course, the exact same argument holds in the opposite direction, right? If I take A to the power of A inverse, well, actually, is that what I want to do here? Let me think. Yeah, and just basically the opposite direction is also true. What do I want to say here? How am I going to parse this together? So I'm going to take A to the order of A inverse, and then maybe I'll write this as A inverse inverse to the order of A inverse. So that's going to give me, I'm sorry, there's so many like A inverses in here, right? But eventually you can get it down to E. And so again, now, thus the order of A divides A inverse. And now I have the double divisibility, right? So that tells me that A is equal to A inverse. Like so. Okay. Does that one make sense? Right? Just show that if you take A to the power of A inverse, you get the identity. If you take A inverse to the power of A, you get the identity. And so they actually had to have the exact same order. For B, B is actually even easier because you're trying to show that these two sets are equal. And I really don't think there's much to do. Clearly, A is in the subgroup generated by A inverse. So that gives you this inclusion. And vice versa. Thus, they're equal. Right, and we're done. So that's all there is to that. That, again, I think is kind of like, oh man, that seems like a lot of work to prove something that was obvious. But that's kind of like how it goes, right? Sometimes the easy proofs are not as obvious as they seem like they should be. But are there any questions about that? Maybe let me zoom out and see if I can give you both these at the same time. Okay, any questions? No, everyone's happy? Okay. Well, if you're happy, then I'm happy. So that's going to take care of it today. Hopefully that made sense. Again, try question 2 on your own. Just make sure that you can reason through it. It's, again, just any hints for question 2, really just start writing stuff out. So certainly A is in, like, for question 2, you kind of want to do a double subset inequality as well, right? So you're trying to show okay, so this direction is immediate, right? Because each of those things on the right is a word, right? So remember, the thing on the left-hand side is the collection of all possible words you can make, assuming that A squared is the identity is equal to B squared, which is the identity, and AB squared is the identity. So the fact that you get this subset inclusion is immediate because all those things on the right are words. Now what you want to show is that every single word on the left-hand side can be reduced to one of those 4 things. Okay, so what do words typically look like? Well, A is certainly a word, B is a word, AB is a word. All right, what's interesting? We know that A is equal to A inverse, we know that B is equal to B inverse, and we know that AB is equal to the identity. So in particular, that means that AB is equal to B inverse A inverse, which is equal to BA, okay? So A and B also commute with each other. And so now what sort of words are we gonna get? We're gonna get ABA is a word. What is ABA equal to? B, exactly. Okay, what's BAB equal to? A. And every other, right? So I've now taken all of the, and I guess I should say BA is equal to AB. So we've got the 1-letter words, the 2-letter words, all the 3-letter words reduced to 1-letter words. And now you basically argue by induction. You say, assume that all the N-letter words are equivalent to either the 1 or 2-letter words, right? And then show that, therefore, the N-letter words are all either a 1-letter word or a 2-letter word themselves. As far as I'm concerned, the proof is now evident from this fact that basically, right, there are no other words. There are no other 3-letter words. Do you agree? Because other 3-letter words will have 2 A's beside each other, which will be the identity, or 2 B's beside each other, which will be the identity. So the only non-trivial words look like A, B, A, B, A, B, A, B, A, B. And you can either argue that they collapse or use the fact that A and B commute to say, look, I can smush together, right? These are the only non-trivial words because, again, if 2 A's or 2 B's beside each other, they're the identity. Well, now I can just collect all the B's together into some collection of B's and A's, but then I know B squared and A squared is equal to the identity. So, only 1 or 0 of the B's and the A's survive in either time. So this is going to be either equal to 1 of A, B, E, or A, B. Do you know what I mean? Like that sort of argument could work. So you can either do it by induction, or you can say, write down an arbitrary word. I know that A and B commute, smush them all together so that all the A's are together and all the B's are together, and then argue that the only 4 things that could happen once you've used the fact that A squared is the identity and B squared is the identity is that 0 or 1 of A and B survive, and that gives you those 4 options. Does that make sense in terms of a hint? Okay, cool. All right, everyone. So yeah, hopefully that helps you out. Try it both ways. Like if you want to do it by induction, totally. And otherwise, if you want to kind of reduce it, I mean, really, you should kind of do it by induction, even in this reduction argument. But it's one of those things that I would say, like, it's pretty clear what's going on, even if you don't directly use induction. But it is what it is. Otherwise, everyone, yeah, thanks so much. Have a good weekend. Don't forget your test. Or I think your assignment's actually due today, right? So get on that. I will probably watching Piazza for the next hour or so, but I won't be watching it for much more after that. So if you have any questions, make sure you get them in. Otherwise, have a good weekend, and I'll see you all next week. Thanks, everyone. See you later.